Good afternoon, everybody. We are here for a very impromptu solar session because everyone's in lockdown, and some children have finished their schoolwork for the day and haven't got much else to do. So we're trying to entertain as much as we can, and Russell graciously offered to do some solar viewing this afternoon so we could have a look at the sun and see what activity was happening on there. So Russ, would you like to run through your equipment again?
Well, thank you very, very much, Mark, for that introduction. And it's always nice to have some clear skies for observing the sun. Always makes it a far more enjoyable presentation. So, Mark, if you wouldn't mind showing the first image.
Got that up nicely.
Yeah, that's very, very good. I can't actually see that at the moment.
Okay. That's okay.
No, there we go. Right. So here we have the setup pretty much as it appears right now on my apartment balcony, only 6 k's from the centre of Melbourne. We have the telescope. Just looks like any old standard refracting telescope with lenses up the front. But almost at the end of the telescope is a very, very important optic. And I don't know, can you see my cursor at all? Moving?
No, we can't.
Okay, never mind. Anyway, towards the end of the telescope is a very, very important optic which gets rid of 99.999% of the sun's light and its heat to allow the beautiful red color of hot hydrogen gas called hydrogen alpha to come through very, very safely to our eye. So, Mark, at the very, very at the very, very end here we have a video camera. As you can see, 2 USB cables to a laptop, and that laptop is connected to the internet. So we will be seeing what the video camera sees in the beautiful light of hydrogen. Now, the video camera is a monochrome camera, so only shows shades of grey. However, it just so happens that the eye is very, very sensitive to these shades of grey. So the views actually in grey are a little bit more contrasty than they would have been in the red light. So although we don't see the colour, nevertheless it is an advantage for online streaming of the sun. So here is an image of the sun with colour added later on. If you just go to the next one, Mark, with the annotated version.
Yes, I can. Here we go.
Which shows a warning. So, ladies and gentlemen, please never ever look at the sun either with your bare eyes or through binoculars or a telescope unless everything is suitably protected against the brilliant light of the sun, and most importantly, the heat of the sun. It is the heat of the sun which does the damage to the eyes. So please, if you have any doubt about the equipment that you're using, whether it's safe for observing the sun, don't do it. Seek, I was going to say professional advice, but we're all amateurs in the Astronomical Society of Victoria. But please consult someone who knows about safe solar viewing, such as myself or many folk within the Astronomical Society of Victoria. Your eyes are very, very valuable, and no way do we wish anyone to damage their eyes through inappropriate observing of the sun. Okie dokie. So with that in mind, let's...
we need to share your program.
Yep, I'll have to do it again then. Right, let us share. So I'll show you what I'm seeing on my screen here. Hold on a minute.
It's okay.
Here we go.
Not quite there yet.
Nope.
We had it. I saw it there before, Russ.
I know. Okay. Should be there now. Here we go.
Yeah, here we go.
Here we go. So you're looking at my laptop screen, ladies and gentlemen, and the video is working, and we're looking at the sun, but hang on, scratching my head. Where's the sun?
Can't see it.
That is a bit of an anticlimax, isn't it? Crikey. Okay, so I see what I've done here. I've got the exposure turned all the way down. So I'm just going to increase the exposure a little bit. Oh, there we are. There's the sun in the top left corner of my screen. So I'm going to use the mounts slow motion controls. And unfortunately, I forgot to mention when we were showing the view of the setup that the telescope is on a mount which is tracking the sky. So that should help the sun to stay in the field of view for a long, long time. In fact, the sun has been in this position here for about an hour. So it means that the mount is doing a pretty good job in keeping the sun within the field of view. So I'm just moving the sun to center it within the field of view now. Very, very quickly she goes.
While you're doing that, Russ.
Yes.
Kirsty Austin wants to know what the telescope is called.
Right. As in the manufacturer's name?
Well, yeah. What's the equipment called that you're using? So it's the Lunt, isn't it?
Called a Lunt. It's made by a company in the US called Lunt, and they manufacture state-of-the-art solar telescopes. They're expensive and they can only be used for solar observing, but they are the best. Well, in many people's minds, they manufacture the best solar telescopes that are available, state-of-the-art. So I hope that answers the question.
I think it did.
So there we are. Here's our sun centering in the field of view. Fantastic. So what can we see? Well, let's turn up the... Fortunately, I can't see the screen so well. And we can turn up the exposure just a little bit more.
There's a little bit of activity on the front of the sun there up the top.
Now notice, Mark, the filament that we saw yesterday has gone. All right, so a filament is a prominence that is silhouetted against the solar disk. But I'll just focus in on this area here just by drawing a little field of view line around it, and we can zoom in. Here we go, and I can make that bigger, make it very big actually. And so there we have a little bit of structure on the sun, and hopefully, ladies and gentlemen, you can see that the sun is moving around, wiggling around a little bit. That is not the sun doing that. That is the Earth's atmosphere. Naturally, we're doing this during daytime when the sun is shining on the Earth's surface. The Earth's surface, buildings, land, is picking up the sun's heat and re-radiating it into the atmosphere, causing heat currents to rise up. And so therefore, looking at the sun through these rising currents of air, that tends to, it's called turbulence, and it tends to make the objects move around a little bit, and we call that seeing. So daytime seeing is not the best, but nevertheless, hopefully you're getting some good views there. I'll just adjust the focus a little bit. It should go from blurry. So you say when, Mark? When you reckon
keep going.
It's sharp.
A little bit more. I don't think you'll get much sharper than that today.
Fair enough. There we go.
Yeah.
So, ladies and gentlemen, you can see some light and shade. So, light and shade is indicative of slightly different temperatures in this layer of the sun that we're looking at. And this layer of the sun that we're looking at, this so-called hydrogen alpha layer, has a special name. It's called the chromosphere, from the Greek chromos, meaning color. So this layer is a red-colored layer called the chromosphere, and it lies slightly above the brilliant layer that we see in the sun during the daytime. That is called the photosphere. So there are a number of different layers on the sun, each layer giving off light of a different color and different intensity. So hydrogen alpha telescope is selecting the chromospheric light, the red light of hydrogen, and allows us to see these wonderful structures. Now, please, why are we seeing regions of slightly different temperature? Well, please bear in mind that the sun's energy comes from the core, which is deep down in the middle of the sun. And as the energy, which is as light, struggles to get to the surface, it reaches a region of the sun where convection takes place. So that means that the energy is transferred by hot gas rising up, and as it rises up, it cools down, becomes less dense. When it reaches the surface, it's now cooler, a little bit less dense, so it wants to sink down towards the center of the sun again. So the brighter regions there are the hotter gas that is rising up, and the darker boundaries are the now slightly cooler gas sinking back down. And so that's why we see the mottled appearance on the sun. And there's a feature here which is probably the remnant of the filament that we saw yesterday.
It's a lot smaller today, isn't it?
Smaller, yes, indeed. So that is a larger area of slightly cooler gas, and really by hot or cold, in the context of what I'm describing here, it's only a few hundred degrees Celsius. This region overall is about 5,000 degrees Celsius, and we're looking at differences in temperature of only about 100 degrees in 5,000 degrees, causing this mottled appearance. So really, yes, go on, Mark.
We have a question. When will the sun die?
We had a similar question yesterday, and please do not lose any sleep over it. Okay, like everything in the universe, everything gets born somehow or other, and everything will eventually die. And the sun is about halfway through its life, if we can call it that. And the best evidence that we have is that the sun formed about 4,600 million years ago. That's 4.6 billion years ago, and it's about halfway through its existence. So it's probably got another 5,000 million years to go of a total life of about 10 billion years. Now, I don't want to go into how we know this because it's quite complicated, but yep, so the sun will die in stages. It's not like it'll be living one day and dead the next, not like people, for example, but the sun will go through a later stage in its life where it will slowly, over a few billion years, suffer changes which will ultimately lead to it no longer being a star in the sense of how we see it today. So I hope that answers your question.
That was a very good answer. Very detailed.
Well, it's hard not to provide some details. So, okay, let's, okay, we're looking at this feature, but I really would like to go back to looking at the whole disk of the sun once again. And here we go. There's the disk of the sun. Now we're looking at this object, our very own star, ladies and gentlemen. An object which is of the same category of objects that we see every night when it's clear. All those stars in the sky. Our sun is just a representative of that class of objects which we call stars. And stars create their own light, their own energy through nuclear reactions in the cores of these things that we call stars. And okay, we see the moon, and we see planets in this of our solar system in the sky as well. But the moon and the planets, they shine by reflecting sun's light back to us. So planets do not shine by their own light, but they act as mirrors, reflecting the sunlight back to us. So that is a very one way of differentiating between stars and planets. There are other ways of doing it, but stars make their own light. Planets and the moon, they just act as mirrors and reflecting light to us. So when we see the sun here, and actually we're losing a sense of scale and proportion, because the diameter of the sun, if we can put it in kilometer terms, it's 1.4 million kilometers across. 1.4 million kilometers across. to put it into another way of comparison, we could fit 109 Earths across the diameter of the sun. 109 Earths would fit across here. That doesn't necessarily mean that the Earth is small. Anyone who's traveled in an aeroplane for 24 hours just to get from halfway around the planet will realize this is quite big. But the sun is huge compared with the Earth. And 109 Earths will fit across there, and it means that over 1 million Earths will fit inside the volume of the sun. 1 million Earths will fit in there, and that's big.
That is big.
But as stars go, the sun is only slightly above average in size. There are stars which are much bigger than the sun, and there are lots and lots of stars which are actually smaller than the sun. So our sun sits a little bit above the middle as far as size goes. And just following on from that question about how long the sun will live, the ages of stars depend critically on one factor, and that is their mass, how much stuff they were able to collect before they started life as stars. And it is a fact that the more massive a star is, and we talk of stars' masses ranking the sun's mass as equal to 1 solar mass, and so there are stars up to about 200 solar masses that we know of, and stars down to about 1/10 of a solar mass. And we know that stars which are more massive than the sun, let's say 100 solar masses, these stars are very, very rare, but they may only live for 1 or 2 million years. Remember, the sun will live for for about 10 billion years in total, but stars which are much more massive than the sun, up to about 100 or 200 solar masses, they will only live for 1 or 2 million of years. And then on the other end of the scale, stars which are much less massive than the sun, of about 1/10 of a solar mass, they will almost live forever because they're using up their fuel so slowly that the fuel that they have will last a long, long time. So I'm talking about fuel, and what is fuel? Well, fuel for stars is hydrogen. In the cores of these stars, the hydrogen is fused together to make helium, and a lot of energy is given out. So why does this process take place? Because gravity is trying to crush stars out of existence. Gravity is always attracting, and as you can see here on the screen, although the sun looks like a circle, it's actually a huge sphere, three-dimensional.
So, Russ, we have a couple of questions that you might be able to answer, because it's on the topic of what you're talking about. So when you're talking about the size of the sun, is how big is the core?
A wonderful question. And unfortunately, we can't actually look inside the sun to work out how big the core is. But according to models, etc., the core will be about 20% to 25%, maybe 30% of the sun's diameter. So, okay, the sun is about 1.4 million kilometers across. So the core will be maybe 20-25% of that that diameter inside there. And because the core is incredibly massive, and gravity wants to try to crush the sun out of existence, ultimately, when a star forms, the core becomes dense enough and hot enough for nuclei of atoms of hydrogen to collide together and ultimately fuse into helium, giving off a lot of energy. And that outward flowing energy ultimately can balance the inward crush of gravity. And when that happens, a star is born. Okay, so hopefully that answers the question. Is there another question there, Mark?
There is. Yeah, there's two more, actually. So we have one from Tony. Would solar flares be visible at this field of view?
Well, they will certainly be visible. Now, there's a lot of confusion about what solar flares are. So solar flares are actually explosions on the sun, which cause outward flows of solar stuff. And we see those outward flows as as what we call prominences. Now, I will show you some prominences as we talk, because that's a wonderful lead into this. Now, prominences tend to be quite a deal fainter than the chromosphere that we're looking at, but let's increase the exposure on our camera here right up to the max, and now we're overexposing the visible surface of the sun, and I'll increase the gain as well, and we'll see some prominences appear on the edge of the sun, up here in particular. Here we go. So these are what we call prominences, and they are the results of flares or little explosions on the sun which have blasted solar stuff into space. And so there's not much else there actually, but I'll crank the gain up a little bit more. A little bit too much. And you can see we're seeing quite a lot of haze around the sun. That's because we're looking through high cloud, ladies and gentlemen, which tends to scatter the sun's light, loses sharpness. But we'll just crank the gain back a little bit to about there. And now I will draw a box around those prominences, and we can have a closer look at them. There we are, and let's go for broke. Bing! There we are. Now I can crank back on the exposure till we get to a stage where those prominences look pretty impressive indeed. So we've got one prominence here, a little bit of wispy stuff there, and a jet coming out. So as I repeat, these prominences are a result of tiny flares on the sun, sites of explosions, release of explosive energy, and that blows solar stuff into space. And they stay up there for some time because the sun is a huge magnet, and this solar stuff becomes magnetized, and the solar stuff tends to be supported by the magnetic lines of force up there, and these things hang around for a little while. So as I mentioned, we saw a wonderful collection of prominences yesterday, and we can have a look at what's left of them later on today. They're still there, but only very, very weakly presented compared with what we saw yesterday. So there we are, our prominences. Now, to put things in perspective,
We've got a couple more questions for you, Russ. You've got them coming through thick and fast at the moment.
Right.
Would you like to hear them first, or do you want to run through what you were going to go through then?
Oh, let's hear them, please.
All right. So Chris is saying our sun is made out of helium and hydrogen. Is this common for most stars, or are there stars made from different elements?
That's a very good question, Chris. And as far as we understand, when the universe was first formed, it was about 25% hydrogen, and the remainder was effectively helium, with a tiny amount of heavier materials, not that much heavier. But that's what stars do in their cores. They take the hydrogen, crush the hydrogen atoms together to produce helium. And from the composition of the sun that we can measure, the sun is about 72% hydrogen, about 27% helium, and that makes 1% left over. And that 1% consists of oxygen and carbon and gold and all the elements that we recognize on planet Earth. So, and stars do have different compositions. This is true because as stars go through their life cycles, they're constantly converting hydrogen into helium. Very big stars, when they get rather old, start converting helium into carbon and oxygen and neon and magnesium. And folks, I can talk dirty like this because I'm a chemist and I understand these elements, and all the way up to iron. Good old iron is ultimately produced in the cores of very massive stars, and once the cores of stars, of these very massive stars, become substantially consisting of iron, then the star must explode as a supernova explosion, because the poor old iron cannot be converted into anything else with the release of energy, And so, anyway, look, I'm straying a little bit off, but
That's okay. We've got some questions that sort of head into that territory.
so I'll just finish up this question. Yes, so stars do have different compositions, because we believe, when I say we, astronomers believe that the sun is what is known as a third generation star, that it consists of stuff that had been processed by two previous generations of stars. And those stars, in their processing, converted hydrogen into helium, helium into carbon, and ultimately, through explosions as supernovae, created all the elements that we see on planet Earth. Because none of the elements that we are made of, the carbon and the oxygen and the calcium, etc., were originally produced in the Big Bang. All these elements have been produced in the cores of stars. So Moby and others have said that we are made of stars, and what a wonderful thing to believe and accept, that that everything we're made of, the iron, for example, as well, were originally produced in the cores of stars or in exploding stars. How phenomenal is that?
Now,
Okay.
Russ,
Yes, is there anyone with us, Mark? Or have
Yeah, we've got lots of questions and lots of people watching. But Sadie, there's a question here that Sadie would like to answer.
Certainly, Sadie.
So the question is, will our sun become a red giant? So Sadie, would you like to answer that?
Well, in approximately 5 billion years, the sun will begin the helium burning process, turning the red giant star. Turning into a red giant star. When it expands, its outer layer will consume Mercury and Venus and reach Earth.
That's a pretty good explanation.
That's a perfect explanation, Sadie. Yes, that is true, and that red giant stage will perhaps start to kick in 2 or 3, maybe 4 billion years from now. So although the sun's got 5 billion years left of its life, the sun as we know it will cease to be a beautiful, normal sort of yellowish star and become a red giant in 2 or 3 or maybe 4 billion years from now. And Earth will therefore no longer will cease to exist as we know it because of that.
So that leads on to another question, Russ.
Yep. Yeah.
Can it become a black hole?
No, it can't.
There you go.
So, for a black hole to form, the core of the star must be the result of an explosion, a supernova explosion, and the core of our sun is just not massive enough to form a black hole. In other words, the sun will not explode when it reaches the end of its life. As Sadie has quite accurately indicated, the sun will become a red giant, and during the red giant phase, the outer layers of the sun will be just wafted into space, just as puffing out stuff. And what will be left of the sun's core will be a white dwarf star, very, very hot. And there are examples of white dwarfs near to us. But no, our sun's core cannot form a black hole because it is not massive enough to do that.
So I've got a very interesting question for you, Russ.
Yep.
Is the Schumann resonance important to us? Someone said it is the sun's heartbeat pulse, but what is it?
Well, that's a remarkably good question, and I can't answer that truly. I consider my knowledge of the sun to be good, but not encyclopedic. So thanks for that. If the questioner could add a little bit of a timescale as to that resonance, is it days or is it years? But no, I can't actually answer that. Perhaps I'd be making things up. But that's a very, very good question. Okay, I'll take that question on notice. Okay, and
there you go. We'll come back to that one.
Yes.
So just another one, bit of a funny one. Helen's been quite funny. If the sun has helium, does that mean it talks in a high voice?
It might very well do so. But anyway.
On a more serious note,
yes.
why can't the sun fuse iron?
Well, see, no stars can fuse iron because iron is the most stable nucleus there is, meaning that to fuse two nuclei of iron together, energy has to actually be put in to the system in order to make a heavier nucleus from fusing iron. And that's no good for the star because stars need to produce energy in order to counteract the constant crushing inward pull of gravity. So when a star gets to a situation where its core consists of iron, the star can do no more because to fuse iron nuclei into heavier elements, that will take energy, and in fact that will lead to the star's complete demise. So once a star's core is predominantly made of iron, that's the end of its energy production, and then gravity takes over and starts crushing firstly the core and then the outer layers of the star into extremely dense states, such as what would ultimately end up as a neutron star or even as a black hole in the extreme circumstances.
Beautiful answer.
So I hope I've answered that right.
That's a good one. So we've got plenty more as well. We've got another one here from
Mark, if I could just one final comment that the sun isn't massive enough to form iron in its core. Once the sun has finished its life cycle, it will consist of a core of mainly carbon and oxygen. And that's as far as it can go. The sun's core just isn't massive enough to fuse carbon or oxygen into heavier elements. That's as far as it can go. There we go.
Well, we have another question.
Yep.
To give perspective, how big would those solar flares be?
Very, very good. That's a wonderful question, and that's something that we always try to provide is some kind of perspective. And I reckon the Earth would fit quite nicely into this region here that I'm outlining with my cursor. Would fit quite neatly. Probably a couple of Earths would fit into that. Just that little blob here and another couple of Earths in that part. So I'd say probably 4, maybe 5 Earths would fit along the length of that prominence. And this one here, a few more, perhaps half a dozen, to put things into perspective. So from the point of view of comparing them to the size of the sun, they're quite small, but comparing these features to the Earth itself, they are several Earths in size. So yes, it's wonderful to put perspective on to things. In fact, I didn't mention that. Okay, I mentioned the size of the sun as being 1.4 million kilometers, but it's also 150 million kilometers away from us. 150 million kilometers. That's how far the Earth is away from the sun, and it takes light 8 minutes and 20 seconds to travel from the sun to the Earth. 8 minutes and 20 seconds, traveling at 300,000 kilometers per second. So that's another way of adding perspective to the Earth's position in our solar system with respect to the sun.
Now, we have an interesting question. It's a request more so than a question.
Wonderful.
Our good friend Neil Creek would like to know if you can do a capture sequence and rough process live for us.
I could do, Neil, but it's a little bit beyond the the remit of these sessions. But I can certainly do a capture, and all I'm going to do is press record. There we go. You can see the rec light is showing up. So I'm now recording that video stream to a video file, and afterwards I can take that video file and convert it into a beautifully sharp still image. So yes, but it's a little bit beyond that, but I'd be happy for an astrophotographic section meeting, for example, to go through how I work up these video frames. I'd be happy to do that. But for a good question. Thanks, Neil.
So we've got, it's a little bit off topic, but you might know the answer. Like Kirsty's wondering if you know of anything smaller than a quark that's not a specific type of quark.
Once again, a wonderful question. And yes, there are things smaller than quarks. Electrons are smaller than quarks. Although when we get down to particles that small, it's often quite hard to define what we mean by size. Particle physicists would say that the electron behaves like it is a point particle, meaning a point has no size. Yet many of the properties of electrons indicate that it must have a finite size, but its size is definitely desperately difficult to measure. And the same goes for quarks, because quarks cannot be produced on their own so that we can measure their size. That quarks are always confined within particles such as protons and neutrons and other things, mesons. So, but to answer your question, quarks will have a physical size if only we could isolate them to measure them, but they'll probably be larger in size than an electron, which for all intents and purposes behaves as a point-like particle, although its properties can only be interpreted as the electron having not being a point particle and having some size associated with it. So that is the problems of quantum mechanics, unfortunately, that some properties say that a particle has this, yet other properties say, well, no, the particle can't have this, it must have that. And it's hard to marry up the two conflicting measurements together. But that's the world in which we live. Full stop.
So we've got more questions for you.
Right.
We've got three more at the moment.
Excellent.
So Robert wants to know, is the sun's core solid or is it a gas? We covered that a little bit earlier. But,
it is definitely a gas, definitely a very, very dense gas and very, very hot. Our best understanding of the conditions in the core is a temperature of about 15 million degrees Kelvin or degrees Celsius. That's 15 million degrees Celsius, and a density about 150 times that of water, so about 150 grams per cubic centimeter. So, and all this is based on models, and unbelievably, the models can be verified by measurements of things like neutrinos and other stuff. So it is quite remarkable. Although we can't actually get a sample of the sun's core, the models predict its properties, and some measurements that we can make of what comes out of the core are very much in agreement with those models.
all right, I think we've got a couple more questions. Very popular today, Russ.
Wonderful. I like popular. That's a change.
How long are the flares that we're currently seeing? So we know that you've fit an Earth inside the bottom of that other one, but how long would they be, these ones?
I reckon at least 3 or 4 Earths would fit along the length of this one. 3 or 4 Earths, and maybe a few more, 5, maybe 6 Earths along that. So they're big. And please bear in mind, they're about 5,000 or so degrees Celsius. So they're pretty hot as well.
Okay, so what have we got? We have, I think that's it. There's our questions.
Fantastic. Well, as I've been answering questions, a few other little bits of information come to mind. And one question is, well, how do we know that the sun is a ball of gas? Well, and not a solid object. Well, we know that because, and we'll be seeing more of these in the next few years, sunspots. Back in the 1850s, astronomers amateur astronomers that is, were very keen on trying to figure out what sunspots are. And I mean, this little dark patch here could end up as a sunspot, but maybe not. But okay, sunspots during the cycles of the sun, lots of sunspots appear over periods of time, but at the moment there are no sunspots on the sun today. But in a week's time, yep, there can be some. But these astronomers noticed that these sunspots weren't stationary. They tended to move across the face of the sun over a period of about 2 weeks. So they would appear over here, and if it was a long-lived sunspot, then the next day it'd be here, and then there the next day. And so over 2 weeks' time, it would pass across the face of the sun and then disappear over the edge of the sun. And they determined it takes about 27 days for a sunspot that is near the sun's equator to do one passage. But of course, sunspots can occur in different positions on the sun. And let's face it, the sun's pole is up about here or thereabouts. But when a sunspot appears closer to the pole, it takes about 30 days to do. About 30 days to do one rotation of the sun. So the sun doesn't rotate as a solid body. In other words, unlike the Earth, where whether you're standing at the equator or 1 foot off the North Pole, it still takes 1 day to do one rotation of the Earth. Whereas for the sun, and it takes different times to do one rotation depending on the position of the sunspot. And from that, it is the only conclusion from that is that the sun is a huge ball of gas and is not a solid body. So
we've got another one here.
Fantastic.
What events will these solar flares cause on Earth?
An excellent question. An excellent question. I'm rubbing my hands together now, just trying to work up an explanation. Well,
put the pressure on you.
No pressure at all. No pressure. Well, we know that the sun gives us heat, gives us light, and gives us gravity as well. Because let's face it, remember the Earth is in orbit around the sun, and although the sun is 150 million kilometers away, the Earth is not removed from some of the worst that the sun can throw at us. And as the questioner very rightly put in the question, solar flares. So these small prominences that we've seen today are the result of very, very small or relatively small solar flares. But we have seen in the past, in historical past, that when large sunspot groups appear, a large sunspot group is indicative of a lot of magnetic energy being stored up, and when that magnetic energy is released explosively, that can send a huge cloud of solar stuff heading towards Earth. And this is called a solar storm, when the Earth passes through this magnetized, charged cloud of solar stuff. And depending on how much stuff there is, how the magnetic field of that moving cloud of gas and dust, interacts with the Earth's magnetic field, it can cause mayhem, not only up in space, but down here on the Earth's surface. So if you have a pen and paper handy, do a Google search of the Carrington event. That's Carrington event in 1859, when one of these huge solar storms passed by Earth, and it caused mayhem down on the Earth's surface. Not only were the northern and southern lights incredibly bright and widespread, but the telegraph system in the US, the poles caught fire, The wires became electrified. Telegraph operators were getting shocks and sparks off the telegraph wires because what was happening, this solar storm, which was happening hundreds of kilometers above the Earth's surface, nevertheless, that impacted what was happening on the Earth's surface itself. So these wires acted like antennae and picked up quite high voltages, and the telegraph operators were getting shocks. So they turned off the power to the telegraph wires, and they were still able to send telegraphic signals through the residual energy that was existing in the system. So these solar storms can be incredibly dangerous to our technology, not only our satellites orbiting the Earth, but also our electrical systems, which are, well, electricity is transported by wires, and so these wires can become overcharged with voltage and can cause breakdown of our electrical systems. And in fact, in 1989, the northeast of North America, around Quebec, the power system grid failed because of a solar storm that was occurring hundreds of kilometers up in space. So imagine what would happen if every region on the Earth was so affected. It would be far worse than COVID from the point of view of breakdown of what we would consider normal in our lives. So imagine living without electricity for months on end because of failure of our electrical systems. It doesn't bear thinking about. And just to finish off, this is the major reason why there are so many probes up there constantly looking at the sun, measuring solar activity, because at least that will give operators here on Earth an hour or two's warning that a solar storm is on its way, so that our electrical systems and our Earth orbiting satellites can be put into safe mode, so that they'll be so the effect on them will be minimized. There will still be effects, but at least the effects will be minimized, especially on our electrical grids here on Earth. So space weather is a very, very important threat to the nice existence that we have here on Earth, because it has happened in the past, in 1859, 1920, 1989, but it will certainly happen again. And that those few hours of warning will be crucial for making as much of our technology safe here on Earth. So, but please don't lose any sleep over it tonight, because it ain't going to happen today. There's nothing on the sun. There has to be a disclaimer here, Mark.
Yes,
there's nothing on the sun at the moment which will cause any fear for space scientists. But the sun's activity, after having gone through a minimum of solar activity late 2019, the sun is heading towards a solar maximum of activity in around 2024, 2025. But nevertheless, activity, there can be spontaneous periods of high activity between now and then and afterwards. So we're heading into a time where the sun will become an increasing threat to us here on Earth. But anyway, please don't lose any sleep over it just now.
So,
well, has everyone stopped? Everyone turned off now?
No, but we do have plenty more questions.
Woo, very good. Right.
So Liam wants to know what filtering, if any, are you using in front of your CCD?
Well, that's a very good question, Liam. And the filtering is in the telescope itself. So it is a hydrogen alpha telescope. So there's a very special optic built into the body of the telescope, which selects the hydrogen alpha wavelength, which is in the deep red of the spectrum that the eye can see, and also a separate filter which removes the infrared light, the heat from the sun's light. And I didn't actually stress in the introduction, it's actually the sun's heat which does the damage to our eyes, not the sun's light. The sun's heat. So the CCD chip is fully protected because it's attached to a scientifically designed and functioning solar telescope. Now I just bumped the telescope and I've moved the sun off the center, but there we are. So yes, the chip is fully protected because it's attached to a solar telescope. Very good question. One other little thing to do.
All right, so
more
questions.
Wonderful.
So David says, given the high rotational speed, is the sun spherical or slightly oblate like the Earth?
Well, it will be slightly oblate, but it takes about 27 days to do one rotation at the equator. But there will be a measure of oblateness, meaning that the diameter of the sun measured pole to pole will be very slightly less than it will be across the equatorial diameter. But I reckon far less than the Earth. But a good question. Very good.
So we have one from our Lunar and Planetary Section Director, Stuart.
Hi, Stuart.
He's online watching, and he said, regarding solar cycle 25, from the evidence we have so far, is this cycle looking quieter than normal or more active?
That's a very, very good question, and gets right to the nub of what's on every solar scientist's lips. At the moment, we don't know what the cycle is going to be like. As Stuart quite rightly says, some solar scientists predict that it's going to be quieter, less active than the previous one. Others are predicting that it's going to be more active. So some will be right, and some will be not so right when we get into solar cycle 25 in full swing. And really, it's only when we do the observations that, when I say we, solar scientists, will know one way or the other. Good question. Right, Mark, more? Oh, have I lost you? Are you there, Mark?
Yeah, sorry. We got a very good question here. Sorry, I was on mute. My apologies. If you bounce a beam of light in a series of mirrors, would the speed of light ever slow down?
I've got to say there are some pretty tough questions coming through here. Crikey, there is. Well, like many things in science, we sometimes forget to qualify what we say. Now, we say that the speed of light is 300,000 kilometers per second, but that is in a vacuum. So when glass passes through things like glass or water or air, the speed of light is slower than its speed in a vacuum because it's now interacting with matter, stuff. So when light bounces between mirrors, let's say that there's air between those mirrors, the speed of light will be less than its speed of light than its speed in a vacuum, because it is passing through a medium, which is not a vacuum. So hopefully that answers your question. And I have to say that materials scientists are actively working on materials that slow the speed of light down so much that it may only be a few kilometers, only a few kilometers per second, or even a few meters per second in that particular medium that the light is passing through. And so that can cause light to do some weird and wonderful things when it's slowed down so much. But yes, when we say it's 300,000 kilometers per second, we should actually say in a vacuum, whatever a vacuum is, because quantum scientists will say there's no such thing as a vacuum. But anyway, that's another story for another time. Okay, this is a solar demonstration, not a quantum mechanics tutorial. Anyway, please, Mark, another question.
We seem to have lost our sun.
We have.
Oh, it's coming back.
We have some heavier cloud going through, so it is indicative of the effects of even relatively thin clouds on the views. But I can change that. I can turn the exposure up, and it'll reappear. There we are. And there we are. We're seeing the clouds passing over now.
So we have another one here. Actually, a couple more questions. So,
wonderful.
If we get a Carrington event or worse, will it knock out our GPS satellites? I can't remember whether you covered that when you answered it before.
It will, yes. It will, unless those satellites have been put into safe mode. It will knock them out, or at least cause our GPS systems to not function because the satellites have been put into safe mode. Absolutely. Certainly, our GPS satellites are they move through the Earth's magnetic field, and so therefore they are vulnerable to the impacts of solar storms passing by. Very much so.
All right, we've got another one. How big was the biggest solar flare ever recorded, and when was it?
Crikey. I have to do a Russ search within my memory here, but
They're trying to stump you, Russ.
They are indeed. They are indeed. Well, flares are measured on a scale from A all the way up to X. So A, B, C, D, M, and X, I think. And X-class flares are the most energetic. And I think and I have to qualify this by saying that this measurement of flares has only been during the space age, when we've had probes up in space that can actually measure the actual energy of these things. But I think the most powerful flare was an X19, and I should also qualify that this is a logarithmic scale, powers of 10. So a B-class flare is 10 times more powerful than an A-class flare, etc. So an X-class flare is about 10,000 times more energetic than an A-class. But anyway, I think there was an X19 flare in 2012 or 2013, something like that. So I think that's probably the most energetic flare that has been measured during the space age. But I feel as though I'm showing off at the moment, and I don't like doing that, especially in public. When I'm on my own, yes, I'm happy to do that, but in public. So there we are.
So before we sort of close it up, so we're just coming on to an hour now. Did you want to have another look and see if we've got those, got some activity happening on the edges of the sun again?
Certainly we can. We have some clouds going through, but that won't deter us. Let's crank up. Bearing in mind those clouds will cause a little bit of diffusion of sun's light, but let's have a look. And crank it up. Very hard to tell. We've got a bit of noise and
oh, they look nice.
Very much, very much. Although this one here, I reckon this little streamer is a new feature.
It looks like a V now.
Yes. A victory sign. I'm pretty sure that's a new feature. Really hard to say. Say the clouds going ahead tends to diffuse the light a little bit, but I have to say, yesterday's demonstration, over half an hour, we saw clear changes to prominences similar to these. Within half an hour, seeing changes. So our sun is a dynamic object. Dynamic meaning always on the change, always on the move.
Wonderful. All right. I think we might leave it there for this session. And if we continue on with lockdown and we're all still a bit bored, we might come back on another sunny day and do it all again, Russ.
We'll certainly do that, and please, even if we're not bored, I'm happy to do it. All right, because our very own star is a beautiful object, always something of interest to look at, and very, very difficult to do it safe observation. And doing it online is absolutely the safest way to do solar observing.
It's a wonderful way to do it.
Wonderful way to do it. Fantastic. So thanks very much, everyone out there, for sharing this solar demonstration with us, courtesy of the Astronomical Society of Victoria, and look forward to speaking with you another time.
Yep, next stream.
Absolutely.
Thanks, everyone.
Thanks very much. Our pleasure. Thank you.